Unit 7 Redox Reactions. Objectives. After studying this unit, you will be able to identify redox reactions as a class of reactions in which oxidation and reduction reactions occur simultaneously. Define the terms oxidation, reduction, oxidant, oxidizing agent, and reductant, reducing agent. Explain mechanism of redox reactions by electron transfer process. Use the concept of oxidation number to identify oxidant and reductant in a reaction. Classify redox reaction into combination, synthesis, decomposition, displacement, and disproportionation reactions. Suggest a comparative order among various reductants and oxidants. Balance chemical equations using 1. Oxidation number, 2. Half reaction method. Learn the concept of redox reactions in terms of electrode processes. Where there is oxidation, there is always reduction. Chemistry is essentially a study of redox systems. Chemistry deals with varieties of matter and change of one kind of matter into the other. Transformation of matter from one kind into another occurs through the various types of reactions. One important category of such reactions is redox reactions. A number of phenomena, both physical as well as biological, are concerned with redox reactions. These reactions find extensive use in pharmaceutical, biological, industrial, metallurgical, and agricultural areas. The importance of these reactions is apparent from the fact that burning of different types of fuels for obtaining energy for domestic, transport, and other commercial purposes, electrochemical processes for extraction of highly reactive metals and nonmetals, manufacturing of chemical compounds like caustic soda, operation of dry and wet batteries, and corrosion of metals fall within the purview of redox processes. Of late, environmental issues like hydrogen economy, use of liquid hydrogen as fuel, and development of ozone hole have started figuring under redox phenomenon. 7.1 Classical idea of redox reactions, oxidation and reduction reactions. Originally, the term oxidation was used to describe the addition of oxygen to an element or a compound. Because of the presence of dioxygen in the atmosphere, approximately 20%, many elements combine with it, and this is the principal reason why they commonly occur on the earth in the form of their oxides. The following reactions represent oxidation processes according to the limited definition of oxidation. 2 Mg solid plus O2 gas gives 2 MgO solid, equation 7.1. S solid plus O2 gas gives SO2 gas, equation 7.2. In reactions 7.1 and 7.2, the elements magnesium and sulfur are oxidized on account of addition of oxygen to them. Similarly, methane is oxidized owing to the addition of oxygen to it. CH4 gas plus 2O2 gas gives CO2 gas plus 2H2O liquid, equation 7.3. A careful examination of reaction 7.3, in which hydrogen has been replaced by oxygen, prompted chemists to reinterpret oxidation in terms of removal of hydrogen from it, and therefore the scope of term oxidation was broadened to include the removal of hydrogen from a substance. The following illustration is another reaction where Removal of hydrogen can also be cited as an oxidation reaction. 2H2S gas plus O2 gas gives 2S solid plus 2H2O liquid, equation 7.4. As knowledge of chemists grew, it was natural to extend the term oxidation for reactions similar to 7.1 to 7.4, which do not involve oxygen but other electronegative elements. The oxidation of magnesium with fluorine, chlorine, and sulfur, etc., occurs according to the following reactions. Mg solid plus F2 gas gives MgF2 solid, equation 7.5. Mg solid plus Cl2 gas gives MgCl2 solid, equation 7.6. Mg solid plus S solid gives Mgs solid, equation 7.7. Incorporating the reaction 7.5 to 7.7 within the fold of oxidation reactions encourage chemists to consider not only the removal of hydrogen as oxidation, but also the removal of electropositive elements as oxidation. Thus, the reaction 2K4 FeCN6 aqueous plus H2O2 aqueous gives 2K3 FeCN6 aqueous plus 2KOH aqueous is interpreted as oxidation due to the removal of electropositive element potassium from potassium ferrocyanide before it changes to potassium ferricyanide. To summarize, the term oxidation is defined as the addition of oxygen or electronegative element to a substance or removal of hydrogen or electropositive element from a substance. In the beginning, reduction was considered as removal of oxygen from a compound. However, the term reduction has been broadened these days to include removal of oxygen or electronegative element from a substance or addition of hydrogen or electropositive element to a substance. According to the definition given above, the following are examples of reduction processes. 2HgO solid gives 2Hg liquid plus O2 gas, equation 7.8. Removal of oxygen from mercuric oxide. 2FeCl3 aqueous plus H2 gas gives 2FeCl2 aqueous plus 2HCl aqueous, equation 7.9. Removal of electronegative element chlorine from ferric chloride. CH2 equals CH2 gas plus H2 gas gives H3C minus CH3 gas 7.10. Addition of hydrogen. 2HgCl2 aqueous plus SnCl2 aqueous gives Hg2Cl2 solid plus SnCl4 aqueous, equation 7.11. Addition of mercury to mercuric chloride. In reaction 7.11, simultaneous oxidation of stannous chloride to stannic chloride is also occurring because of the addition of electronegative element chlorine to it. It was soon realized that oxidation and reduction always occur simultaneously, as will be apparent by re-examining all the equations given above. Hence, the word redox was coined for this class of chemical reactions. Problem 7.1. In the reactions given below, identify the species undergoing oxidation and reduction. 1. H2S gas plus Cl2 gas gives 2HCl gas plus S solid. 2. 3Fe3O4 solid plus 8Al solid gives 9Fe solid plus 4Al2O3 solid. 3. 2Na solid plus H2 gas gives 2NaH solid. Solution. 1. H2S is oxidized because a more electronegative element chlorine is added to hydrogen, or a more electropositive element hydrogen has been removed from S. Chlorine is reduced due to addition of hydrogen to it. 2. Aluminium is oxidized because oxygen is added to it. Ferrous ferric oxide Fe3O4 is reduced because oxygen has been removed from it. 3. With the careful application of the concept of electronegativity only, we may infer that sodium is oxidized and hydrogen is reduced. Reaction 3, chosen here, prompts us to think in terms of another way to define redox reactions. 7.2. Redox reactions in terms of electron transfer reactions. We have already learned that the reactions 2Na solid plus Cl2 gas gives 2NaCl solid, equation 7.12. 4Na solid plus O2 gas gives 2Na2O solid, equation 7.13. 2Na solid plus S solid gives Na2S solid, equation 7.14, are redox reactions because in each of these reactions, sodium is oxidized due to the addition of either oxygen or more electronegative element to sodium. Simultaneously, chlorine, oxygen and sulfur are reduced because to each of these the electropositive element sodium has been added. From our knowledge of chemical bonding, we also know that sodium chloride, sodium oxide, and sodium sulfide are ionic compounds and perhaps better written as Na plus Cl minus solid, Na plus 2 O2 minus solid, and Na plus 2 S2 minus solid. Development of charges in the species produced suggests us to rewrite the reactions 7.12 to 7.14 in the following manner. 2Na solid plus Cl2 gas gives 2Na plus Cl minus solid. 2Na loses 2 electrons. Cl2 gains 2 electrons. 2Na solid plus O2 gas gives Na plus 2 O2 minus solid. 2Na loses 2 electrons. O2 gains 2 electrons. 2Na solid plus S solid gives Na plus 2 S2 minus solid. 2Na loses 2 electrons. S gains 2 electrons. For convenience, each of the above processes can be considered as two separate steps, one involving the loss of electrons and the other the gain of electrons. As an illustration, we may further elaborate one of these, say the formation of sodium chloride. 2Na solid gives 2Na plus gas plus 2 electrons. Cl2 gas plus 2 electrons gives 2Cl minus gas. Each of the above steps is called a half reaction, which explicitly shows involvement of electrons. Sum of the half reactions gives the overall reaction. 2Na solid plus Cl2 gas gives 2Na plus Cl minus solid or 2NaCl solid. Reactions 7.12 to 7.14. suggests that half reactions that involve loss of electrons are called oxidation reactions. Similarly, the half reactions that involve gain of electrons are called reduction reactions. It may not be out of context to mention here that the new way of defining oxidation and reduction has been achieved only by establishing a correlation between the behavior of species as per the classical idea and their interplay in electron transfer change. In reactions 7.12 to 7.14, sodium, which is oxidized, acts as a reducing agent because it donates electron to each of the elements interacting with it and thus helps in reducing them. Chlorine, oxygen, and sulfur are reduced and act as oxidizing agents because these accept electrons from sodium. To summarize, we may mention that oxidation, loss of electrons by any species; reduction, gain of electrons by any species; oxidizing agent, acceptor of electrons; reducing agent, donor of electrons. Problem 7.2. Justify that the reaction 2Na solid plus H2 gas giving 2NaH solid is a redox change. Solution. Since in the above reaction, the compound formed is an ionic compound, which may also be represented as Na plus H minus solid, this suggests that one half reaction in this process is 2Na solid gives 2Na plus gas plus 2 electrons. And the other half reaction is H2 gas plus 2 electrons gives 2H minus gas. This splitting of the reaction under examination into two half reactions automatically reveals that here sodium is oxidized and hydrogen is reduced. Therefore, the complete reaction is a redox change. 7.2.1 Competitive electron transfer reactions. Place a strip of metallic zinc in an aqueous solution of copper nitrate as shown in figure 7.1 for about an hour. You may notice that the strip becomes coated with reddish metallic copper and the blue color of the solution disappears. Formation of Zn2 plus ions among the products can easily be judged when the blue color of the solution due to Cu2 plus has disappeared. If hydrogen sulfide gas is passed through the colorless solution containing Zn2 plus ions, appearance of white zinc sulfide Zns can be seen on making the solution alkaline with ammonia. The reaction between metallic zinc and the aqueous solution of copper nitrate is Zn solid plus Cu2 plus aqueous gives Zn2 plus aqueous plus Cu solid, equation 7.15. In reaction 7.15, zinc has lost electrons to form Zn2 plus and therefore zinc is oxidized. Evidently, now if zinc is oxidized, releasing electrons, something must be reduced, accepting the electrons lost by zinc. Copper ion is reduced by gaining electrons from the zinc. Reaction 7.15 may be rewritten as Zns plus Cu2 plus aqueous gives Zn2 plus aqueous plus Cu solid. Zn releases 2 electrons, Cu2 plus gains 2 electrons. At this stage, we may investigate the state of equilibrium for the reaction represented by equation 7.15. For this purpose, let us place a strip of metallic copper in a zinc sulfate solution. No visible reaction is noticed. An attempt to detect the presence of Cu2 plus ions by passing H2S gas through the solution to produce the black color of cupric sulfide CuS does not succeed. Cupric sulfide has such a low solubility that this is an extremely sensitive test. Yet, the amount of Cu2 plus formed cannot be detected. We thus conclude that the stage of equilibrium for the reaction 7.15 greatly favors the products over the reactants. Let us extend electron transfer reaction now to copper metal and silver nitrate solution in water and arrange a setup as shown in figure 7.2. The solution develops blue color due to the formation of Cu2 plus ions on account of the reaction Cu solid plus 2Ag plus aqueous gives Cu2 plus aqueous plus 2Ag solid. Cu solid releases 2 electrons to form Cu2 plus aqueous. 2Ag plus aqueous gains 2 electrons to form 2Ag solid. Equation 7.16. Here, Cu solid is oxidized to Cu2 plus aqueous and Ag plus aqueous is reduced to Ag solid. Equilibrium greatly favors the products Cu2 plus aqueous and Ag solid. By way of contrast, let us also compare the reaction of metallic cobalt placed in nickel sulfate solution. The reaction that occurs here is Co solid plus Ni2 plus aqueous giving CO2 plus aqueous plus Ni solid. Co solid releases 2 electrons, Ni2 plus gains 2 electrons to form Ni solid. At equilibrium, chemical tests reveal that both Ni2 plus aqueous and CO2 plus aqueous are present at moderate concentrations. In this case, neither the reactants CO and Ni2 plus nor the products CO2 plus and Ni are greatly favored. This competition for release of electrons incidentally reminds us of the competition for release of protons among acids. The similarity suggests that we might develop a table in which metals and their ions are listed on the basis of their tendency to release electrons, just as we do in the case of acids to indicate the strength of the acids. As a matter of fact, we have already made certain comparisons. By comparison, we have come to know that zinc releases electrons to copper and copper releases electrons to silver, and therefore, the electron releasing tendency of the metals is in the order Zn greater than Cu greater than Ag. We would love to make our list more vast and design a metal activity series or electrochemical series. The competition for electrons between various metals helps us to design a class of cells named as galvanic cells in which the chemical reactions become the source of electrical energy. We would study more about these cells in class 12. 7.3 Oxidation Number. A less obvious example of electron transfer is realized when hydrogen combines with oxygen to form water by the reaction. 2H2 gas plus O2 gas gives 2H2O liquid, equation 7.18. Though not simple in its approach, yet we can visualize the hydrogen atom as going from a neutral zero state in H2 to a positive state in H2O. The oxygen atom goes from a zero state in O2 to a di-negative state in H2O. It is assumed that there is an electron transfer from hydrogen to oxygen, and consequently H2 is oxidized and O2 is reduced. However, as we shall see later, the charge transfer is only partial and is perhaps better described as an electron shift rather than a complete loss of electron by hydrogen and gain by oxygen. What has been said here with respect to equation 7.18 may be true for a good number of other reactions involving covalent compounds. Two such examples of this class of the reactions are H2 solid plus Cl2 gas giving 2HCl gas, equation 7.19, and CH4 gas plus 4Cl2 gas giving CCl4 liquid plus 4HCl gas, equation 7.20. In order to keep track of electron shifts in chemical reactions involving formation of covalent compounds, a more practical method of using oxidation number has been developed. In this method, it is always assumed that there is a complete transfer of electron from a less electronegative atom to a more electronegative atom. For example, we rewrite equations 7.18 to 7.20 to show charge on each of the atoms forming part of the reaction. 2H2 gas plus O2 gas giving 2H2O liquid, H2 0, O2 0, 2H2 plus 1, O minus 2, equation 7.21. H2 solid plus Cl2 gas giving 2HCl gas, H2 0, Cl2 0, 2H plus 1, Cl minus 1, equation 7.22. CH4 gas plus 4Cl2 gas giving CCl4 liquid plus 4HCl gas, equation 7.23. C minus 4 H4 plus 1 4Cl2 0, C plus 4 Cl4 minus 1 4H plus 1 Cl minus 1. It may be emphasized that the assumption of electron transfer is made for bookkeeping purpose only, and it will become obvious at a later stage in this unit that it leads to the simple description of redox reactions. Oxidation number denotes the oxidation state of an element in a compound ascertained according to a set of rules formulated on the basis that electron pair in a covalent bond belongs entirely to more electronegative element. It is not always possible to remember or make out easily in a compound or ion which element is more electronegative than the other. Therefore, a set of rules has been formulated to determine the oxidation number of an element in a compound or ion. If two or more than two atoms of an element are present in the molecule or ion, such as Na2S2O3, or Cr2O7 raised to 2 minus, the oxidation number of the atom of that element will then be the average of the oxidation number of all the atoms of that element. We may at this stage state the rules for the calculation of oxidation number. These rules are: 1. In elements in the free or the uncombined state, each atom bears an oxidation number of 0. Evidently, each atom in H2, O2, Cl2, O3, P4, S8, Na, Mg, Al has the oxidation number 0. 2. For ions composed of only one atom, the oxidation number is equal to the charge on the ion. Thus, Na plus ion has an oxidation number of +1, Mg2 plus ion +2, Fe3 plus ion +3, Cl minus ion -1, O2 minus ion -2, and so on. In their compounds, all alkali metals have oxidation number of +1, and all alkaline earth metals have an oxidation number of +2. Aluminum is regarded to have an oxidation number of +3 in all its compounds. 3. The oxidation number of oxygen in most compounds is -2. However, we come across two kinds of exceptions here. One arises in the case of peroxides and superoxides, the compounds of oxygen in which oxygen atoms are directly linked to each other. While in peroxides, for example H2O2, Na2O2, each oxygen atom is assigned an oxygen number of -1. In superoxides, for example KO2, RbO2, each oxygen atom is assigned an oxidation number of -1/2. The second exception appears rarely, that is, when oxygen is bonded to fluorine. In such compounds, example, oxygen difluoride OF2 and dioxygen difluoride O2F2, the oxygen is assigned an oxidation number of +2 and +1 respectively. The number assigned to oxygen will depend upon the bonding state of oxygen, but this number would now be a positive figure only. 4. The oxidation number of hydrogen is +1, except when it is bonded to metals in binary compounds, that is, compounds containing two elements. For example, in LiH, NaH, and CaH2, its oxidation number is -1. 5. In all its compounds, fluorine has an oxidation number of -1. Other halogens, chlorine, bromine, and iodine, also have an oxidation number of -1 when they occur as halide ions in their compounds. Chlorine, bromine, and iodine, when combined with oxygen, for example, in oxoacids and oxoanions, have positive oxidation numbers. 6. The algebraic sum of the oxidation number of all the atoms in a compound must be 0. In polyatomic ion, the algebraic sum of all the oxidation numbers of atoms of the ion must equal the charge on the ion. Thus, the sum of oxidation number of 3 oxygen atoms and 1 carbon atom in the carbonate ion CO3 2- must equal -2. By the application of the above rules, we can find out the oxidation number of the desired element in a molecule or in an ion. It is clear that the metallic elements have positive oxidation number and non-metallic elements have positive or negative oxidation number. The atoms of transition elements usually display several positive oxidation states. The highest oxidation number of a representative element is the group number for the first two groups and the group number -10 following the long form of periodic table for the other groups. Thus, it implies that the highest value of oxidation number exhibited by an atom of an element generally increases across the period in the periodic table. In the third period, the highest value of oxidation number changes from 1 to 7 as indicated below in the compounds of the elements. A term that is often used interchangeably with the oxidation number is the oxidation state. Thus, in CO2, the oxidation state of carbon is +4, that is also its oxidation number, and similarly the oxidation state as well as oxidation number of oxygen is -2. This implies that the oxidation number denotes the oxidation state of an element in a compound. The oxidation number or state of a metal in a compound is sometimes presented according to the notation given by German chemist Alfred Stock. It is popularly known as Stock notation. According to this, the oxidation number is expressed by putting a Roman numeral representing the oxidation number in parentheses after the symbol of the metal in the molecular formula. Thus, Aurous chloride and auric chloride are written as Au1Cl and Au3Cl3. Similarly, stannous chloride and stannic chloride are written as Sn2Cl2 and Sn4Cl4. This change in oxidation number implies change in oxidation state, which in turn helps to identify whether the species is present in oxidized form or reduced form. Thus, Hg2,1Cl2 is the reduced form of Hg2Cl2. Problem 7.3. Using Stock notation, represent the following compounds: HAuCl4, Tl2O, FeO, Fe2O3, CuI, CuO, MnO, and MnO2. Solution. By applying various rules of calculating the oxidation number of the desired element in a compound, the oxidation number of each metallic element in its compound is as follows. HAuCl4 gives Au has 3, Tl2O gives Tl has 1, FeO gives Fe has 2, Fe2O3 gives Fe has 3, CuI gives Cu has 1, CuO means Cu has 2, MnO means Mn has 2, MnO2 means Mn has 4. Therefore, these compounds may be represented as HAu3Cl4, Tl2,1O, Fe2O, Fe2,3O3, Cu1I, Cu2O, Mn2O, Mn4O2. The idea of oxidation number has been invariably applied to define oxidation, reduction, oxidizing agent oxidant, reducing agent reductant, and the redox reaction. To summarize, we may say that oxidation an increase in the oxidation number of the element in the given substance. Reduction, a decrease in the oxidation number of the element in the given substance. Oxidizing agent, a reagent which can increase the oxidation number of an element in a given substance. These reagents are called as oxidants also. Reducing agent, a reagent which lowers the oxidation number of an element in a given substance. These reagents are also called as reductants. Redox reactions, reactions which involve change in oxidation number of the interacting species. Problem 7.4. Justify that the reaction 2Cu2O solid plus Cu2S solid gives 6Cu solid plus SO2 gas is a redox reaction. Identify the species oxidized or reduced, which acts as an oxidant and which acts as a reductant. Solution. Let us assign the oxidation number to each of the species in the reaction under examination. This results into 2Cu2O solid plus Cu2S solid gives 6Cu solid plus SO2. Cu2 plus 1 O minus 2 Cu2 plus 1 S minus 2 gives Cu0 S plus 4 O minus 2. We therefore conclude that in this reaction, copper is reduced from +1 state to 0 oxidation state, and sulfur is oxidized from -2 state to +4 state. The above reaction is thus a redox reaction. Further, Cu2O helps sulfur in Cu2S to increase its oxidation number. Therefore, Cu1 is an oxidant, and sulfur of Cu2S helps copper both in Cu2S itself and Cu2O to decrease its oxidation number. Therefore, sulfur of Cu2S is reductant. 7.3.1 Types of redox reactions. 1. Combination reactions. A combination reaction may be denoted in the manner A plus B gives C. Either A and B or both A and B must be in the elemental form for such a reaction to be a redox reaction. All combustion reactions which make use of elemental dioxygen as well as other reactions involving elements other than dioxygen are redox reactions. Some important examples of this category are C solid, C0 plus O2 gas, O2 0 gives CO2 gas, C plus 4, O2 minus 2, equation 7.24. 3 Mg solid, Mg0 plus N2 gas, N2 0 gives Mg3 N2 solid, Mg plus 2, N2 minus 3, equation 7.25. CH4 gas, C minus 4, H plus 1 plus 2O2 gas, O2 0 gives CO2 gas, C plus 4, O2 minus 2 plus 2H2O liquid, H2 plus 1, O minus 2. 2. Decomposition reactions. Decomposition reactions are the opposite of combination reactions. Precisely, a decomposition reaction leads to the breakdown of a compound into two or more components, at least one of which must be in the elemental state. Examples of this class of reactions are 2H2O liquid, where H2 plus 1 O minus 2 gives 2H2 gas 0 plus O2 gas 0, equation 7.26. 2NaH solid, where Na plus 1 H minus 1 gives 2Na solid 0 plus H2 gas 0, equation 7.27. 2KClO3 solid, where K plus 1 Cl plus 5 O3 minus 2 gives 2KCl solid, where K plus 1 Cl minus 1 plus 3O2 gas, where O2 0, equation 7.28. It may be carefully be noted that there is no change in the oxidation number of hydrogen in methane under combination reactions, and that of potassium in potassium chlorate in reaction 7.28. This may also be noted here that all decomposition reactions are not redox reactions. For example, decomposition of calcium carbonate is not a redox reaction. CaCO3 solid, Ca plus 2, C plus 4, O3 minus 2 gives CaO solid, Ca plus 2, O minus 2 plus CO2 gas, where C plus 4, O2 minus 2. 3. Displacement reactions. In a displacement reaction, an ion or an atom in a compound is replaced by an ion or an atom of another element. It may be denoted as X plus YZ gives XZ plus Y. Displacement reactions fit into two categories: metal displacement and non-metal displacement. A. Metal displacement. A metal in a compound can be displaced by another metal in the uncombined state. We have already discussed about this class of reactions under section 7.2.1. Metal displacement reactions find many applications in metallurgical processes in which pure metals are obtained from their compounds in ores. A few such examples are CuSO4 aqueous, Cu plus 2, S plus 6, O4 minus 2 plus zinc solid, zinc 0 gives Cu solid 0 plus ZnSO4 aqueous, Zn plus 2, S plus 6, O4 minus 2, equation 7.29. V2O5 solid, V2 plus 5, O5 minus 2 plus 5Ca solid, Ca0 gives 2V solid, V0 plus 5CaO solid, Ca plus 2, O minus 2, equation 7.30. TiCl4 liquid, Ti plus 4, Cl4 minus 1 plus 2Mg solid, Mg0 gives Ti solid plus 2 plus 2MgCl2 solid, equation 7.31. Cr2O3 solid, Cr2 plus 3, O3 minus 2 plus 2Al solid, Al0 gives Al2O3 solid plus 2Cr solid. Equation 7.32. In each case, the reducing metal is a better reducing agent than the one that is being reduced, which evidently shows more capability to lose electrons as compared to the one that is reduced. B. Non-metal displacement. The non-metal displacement of redox reactions include hydrogen displacement and a rarely occurring reaction involving oxygen displacement. All alkali metals and some alkaline earth metals, Ca, Sr and Ba, which are very good reductants, will displace hydrogen from cold water. 2Na solid Na0 plus 2H2O liquid H2 plus 1 O minus 2 gives 2NaOH aqueous Na plus 1 O minus 2 H plus 1 plus H2 gas H2 0. Equation 7.33. Ca solid Ca0 plus 2H2O H2 plus 1 O minus 2 liquid gives CaOH2 aqueous Ca plus 2 O minus 2 H plus 1 plus H2 gas H2 0. Equation 7.34. Less active metals such as magnesium and iron react with steam to produce dihydrogen gas. Mg solid Mg0 plus 2H2O liquid H2 plus 1 O minus 2 gives MgOH2 solid Mg plus 2 O minus 2 H plus 1 plus H2 gas H2 0. Equation 7.35. 2 Fe solid Fe0 plus 3H2O liquid H2 plus 1 O minus 2 gives Fe2O3 solid Fe2 plus 3 O3 minus 2 plus 3H2 gas H2 0. Equation 7.36. Many metals, including those which do not react with cold water, are capable of displacing hydrogen from acids. Dihydrogen from acids may even be produced by such metals which do not react with steam. Cadmium and tin are the examples of such metals. A few examples for the displacement of hydrogen from acids are Zn solid Zn0 plus 2 HCl aqueous H plus 1 Cl minus 1 gives ZnCl2 aqueous Zn plus 2 Cl2 minus 1 plus H2 gas H2 0. Equation 7.37. Mg solid Mg0 plus 2 HCl aqueous H plus 1 Cl minus 1 gives MgCl2 aqueous Mg plus 2 Cl2 minus 1 plus H2 gas H2 0. Equation 7.38. Fe solid Fe0 plus 2 HCl aqueous H plus 1 Cl minus 1 gives FeCl2 aqueous Fe plus 2 Cl2 minus 1 plus H2 gas H2 0. Equation 7.39. Reactions 7.37 to 7.39 are used to prepare dihydrogen gas in the laboratory. Here, the reactivity of metals is reflected in the rate of hydrogen gas evolution, which is the slowest for the least active metal Fe and the fastest for the most reactive metal Mg. Very less active metals which may occur in the native state, such as silver Ag and gold Au, do not react even with hydrochloric acid. In section 7.2.1, we have already discussed that the metals zinc Zn, copper Cu, and silver Ag, through the tendency to lose electrons, show their reducing activity in the order Zn greater than Cu greater than Ag. Like metals, activity series also exist for the halogens. The power of these elements as oxidizing agents decreases as we move down from fluorine to iodine in group 17 of the periodic table. This implies that fluorine is so reactive that it can replace chloride, bromide, and iodide ions in solution. In fact, fluorine is so reactive that it attacks water and displaces the oxygen of water. 2H2O liquid, H2 plus 1 O minus 2 plus 2F2 gas, F2 0, gives 4HF aqueous, H plus 1 F minus 1 plus O2 gas, O2 0. Equation 7.40. It is for this reason that the displacement reactions of chlorine, bromine, and iodine using fluorine are not generally carried out in aqueous solution. On the other hand, chlorine can displace bromide and iodide ions in an aqueous solution as shown below. Cl2 gas Cl2 0 plus 2 kBr aqueous K plus 1 Br minus 1 gives 2 KCl aqueous K plus 1 Cl minus 1 plus Br2 liquid Br 0. Equation 7.41. Cl2 gas Cl2 0 plus 2 Ki aqueous K plus 1 I minus 1 gives 2 KCl aqueous K plus 1 Cl minus 1 plus I2 solid I2 0. Equation 7.42. As Br2 and I2 are colored and dissolve in CCl4, can easily be identified from the color of the solution. The above reactions can be written in ionic form as Cl2 gas Cl2 0 plus 2 Br minus 1 aqueous gives 2 Cl minus aqueous Cl minus 1 plus Br2 liquid Br2 0. Equation 7.41a. Cl2 gas Cl2 0 plus 2 I minus aqueous I minus 1 gives 2 Cl minus aqueous Cl minus 1 plus I2 solid I2 0. Equation 7.42b. Reaction 7.41 and 7.42 form the basis of identifying Br minus and I minus in the laboratory through the test popularly known as layer test. It may not be out of place to mention here that bromine likewise can displace iodide ion in solution. Br2 liquid Br 0 plus 2 I minus aqueous I minus 1 gives 2 Br minus aqueous Br minus 1 plus I2 solid I2 0. Equation 7.43. The halogen displacement reactions have a direct industrial application. The recovery of halogens from their halides requires an oxidation process which is represented by 2x minus gives x2 plus 2e minus. Equation 7.44. Here, X denotes a halogen element, whereas chemical means are available to oxidize Cl minus, Br minus, and I minus, as fluorine is the strongest oxidizing agent. There is no way to convert F minus ions to F2 by chemical means. The only way to achieve F2 from F minus is to oxidize electrolytically, the details of which you will study at a later stage. 4. Disproportionation reactions. Disproportionation reactions are a special type of redox reactions. In a disproportionation reaction, an element in one oxidation state is simultaneously oxidized and reduced. One of the reacting substances in a disproportionation reaction always contains an element that can exist in at least three oxidation states. The element in the form of reacting substance is in the intermediate oxidation state, and both higher and lower oxidation states of that element are formed in the reaction. The decomposition of hydrogen peroxide is a familiar example of the reaction where oxygen experiences disproportionation. 2H2O2 aqueous, H2 plus 1 O2 minus 1 gives 2H2O liquid, H2 plus 1 O minus 2 plus O2 gas, O2 0. Equation 7.45. Here, the oxygen of peroxide which is present in -1 state is converted to 0 oxidation state in O2 and decreases to -2 oxidation state in H2O. Phosphorus, sulfur, and chlorine undergo disproportionation in the alkaline medium as shown below. P4 solid P0 plus 3OH minus aqueous plus 3H2O liquid gives PH3 gas minus 3 plus 3H2PO2 minus plus 1 aqueous gives equation 7.46. S8 solid S0 plus 12OH minus aqueous gives 4S2 minus aqueous minus 2 plus 2S2O3 2 minus aqueous plus 2 plus 6H2O liquid, equation 7.47. Cl2 gas Cl0 plus 2OH minus aqueous gives ClO minus aqueous plus 1 plus Cl minus aqueous minus 1 plus H2O liquid, equation 7.48. The reaction 7.48 describes the formation of household bleaching agents. The hypochlorite ion ClO- formed in the reaction oxidizes the color-bearing stains of the substances to colorless compounds. It is of interest to mention here that whereas bromine and iodine follow the same trend as exhibited by chlorine in reaction 7.48, fluorine shows deviation from this behavior when it reacts with alkali. The reaction that takes place in the case of fluorine is as follows. 2F2 gas plus 2OH minus aqueous gives 2F minus aqueous plus OF2 gas plus H2O liquid, equation 7.49. It is to be noted with care that fluorine in reaction 7.49 will undoubtedly attack water to produce some oxygen also. This departure shown by fluorine is not surprising for us, as we know the limitation of fluorine that Being the most electronegative element, it cannot exhibit any positive oxidation state. This means that among halogens, fluorine does not show a disproportionation tendency. Problem 7.5. Which of the following species do not show disproportionation reaction and why? ClO-, ClO2-, ClO3-, and ClO4-. Also, write reaction for each of the species that disproportionates. Solution. Among the oxo anions of chlorine listed above, ClO4- does not disproportionate because in this oxo anion, chlorine is present in its highest oxidation state, that is, +7. The disproportionation reactions for the other three oxo anions of chlorine are as follows. 3Cl O- Cl plus 1 gives 2Cl- Cl minus 1 plus ClO3- Cl plus 5. 6ClO2- Cl plus 3 with HV gives 4ClO3- Cl plus 5 plus 2Cl- Cl minus 1. 4ClO3- Cl plus 5 gives Cl minus Cl minus 1 plus 3ClO4- Cl plus 7. Problem 7.6. Suggest a scheme of classification of the following redox reactions. A. N2 gas plus O2 gas gives 2NO gas. B. 2PbNO3 solid gives 2PbO solid plus 4NO2 gas plus O2 gas. C. NaH solid plus H2O liquid gives NaOH aqueous plus H2 gas. D. 2NO2 gas plus 2OH minus aqueous gives NO2 minus aqueous plus NO3 minus aqueous plus H2O liquid. Solution. In reaction A, the compound nitric oxide is formed by the combination of the elemental substances nitrogen and oxygen. Therefore, this is an example of combination redox reactions. The reaction B involves the breaking down of lead nitrate into three components. Therefore, this is categorized under decomposition redox reaction. In reaction C, hydrogen of water has been displaced by hydride ion into dihydrogen gas. Therefore, this may be called as displacement redox reaction. The reaction D involves disproportionation of NO2 plus 4 state into NO2 minus plus 3 state and NO3 minus plus 5 state. Therefore, reaction D is an example of disproportionation redox reaction. The paradox of fractional oxidation number. Sometimes we come across certain compounds in which the oxidation number of a particular element in the compound is in fraction. Examples are C3O2, where oxidation number of carbon is 4/3, Br3O8, where oxidation number of bromine is 16/3, and Na2S4O6, where oxidation number of sulfur is 2.5. We know that the idea of fractional oxidation number is unconvincing to us because electrons are never shared or transferred in fraction. Actually, this fractional oxidation state is the average oxidation state of the element under examination, and the structural parameters reveal that the element for whom fractional oxidation state is realized is present in different oxidation states. Structure of the species C3O2, Br3O8, and S4O6 raised to 2- reveal the following bonding situations. The element marked with asterisks in each species is exhibiting the different oxidation state, oxidation number, from rest of the atoms of the same element in each of the species. This reveals that in C3O2, 2 carbon atoms are present in +2 oxidation state each, whereas the third one is present in 0 oxidation state and the average is 4/3. However, the realistic picture is +2 for 2 terminal carbons and 0 for the middle carbon. Likewise, in Br3O8, each of the 2 terminal bromine atoms are present in +6 oxidation state and the middle bromine is present in +4 oxidation state. Once again, the average that is different from reality is 16/3. In the same fashion, in the species S4O6 raised to 2-, each of the 2 extreme sulfurs exhibits oxidation state of +5 and the 2 middle sulfurs as 0. The average of 4 oxidation numbers of sulfurs of the S4O6 2- is 2.5, whereas the reality being +5, 0, 0, and +5 oxidation number respectively for each sulfur. We may thus in general conclude the idea of fractional oxidation state should be taken with care, and the reality is revealed by the structures only. Further, whenever we come across with fractional oxidation state of any particular element in any species, we must understand that this is the average oxidation number only. In reality, revealed by structures, the element in that particular species is present in more than one whole number oxidation states. Fe3O4, Mn3O4, Pb3O4 are some of the other examples of the compounds which are mixed oxides where we come across fractional oxidation states of the metal atom. However, the oxidation states may be in fraction as in O2 plus and O2 where it is +1/2 and -1/2 respectively. Problem 7.7. Why do the following reactions proceed differently? Pb3O4 plus 8HCl giving 3PbCl2 plus Cl2 plus 4H2O and Pb3O4 plus 4HNO3 giving 2PbNO3 2 plus PbO2 plus 2H2O. Solution: Pb3O4 is actually a stoichiometric mixture of 2 mole of PbO and 1 mole of PbO2. In PbO2, lead is present in +4 oxidation state, whereas the stable oxidation state of lead in PbO is +2. PbO2 thus can act as an oxidant, oxidizing agent, and therefore can oxidize Cl- ion of HCl into chlorine. We may also keep in mind that PbO is a basic oxide. Therefore, the reaction Pb3O4 plus 8 HCl giving 3 PbCl2 plus Cl2 plus 4H2O can be split into two reactions, namely 2 PbO plus 4 HCl giving 2 PbCl2 plus 2 H2O acid-base reaction, PbO2 Pb plus 4 plus 4 HCl minus 1 giving PbCl2 plus 2 plus Cl2 0 plus 2 H2O redox reaction. Since HNO3 itself is an oxidizing agent, therefore, it is unlikely that the reaction may occur between PbO2 and HNO3. However, the acid-base reaction occurs between PbO and HNO3 as 2 PbO plus 4 HNO3 giving 2 PbNO3 2 plus 2H2O. It is the passive nature of PbO2 against HNO3 that makes the reaction different from the one that follows with HCl. 7.3.2 Balancing of redox reactions. Two methods are used to balance chemical equations for redox processes. One of these methods is based on the change in the oxidation number of reducing agent and the oxidizing agent, and the other method is based on splitting the redox reaction into two half reactions, one involving oxidation and the other involving reduction. Both these methods are in use, and the choice of their use rests with the individual using them. A. Oxidation number method. In writing equations for oxidation reduction reactions, just as for other reactions, the compositions and formulas must be known for the substances that react and for the products that are formed. The oxidation number method is now best illustrated in the following steps. Step 1. Write the correct formula for each reactant and product. Step 2. Identify atoms which undergo change in oxidation number in the reaction by assigning the oxidation number to all elements in the reaction. Step 3. Calculate the increase or decrease in the oxidation number per atom and for the entire molecule or ion in which it occurs. If these are not equal, then multiply by suitable number so that these become equal. If you realize that two substances are reduced and nothing is oxidized or vice versa, something is wrong. Either the formulas of reactants or products are wrong, or the oxidation numbers have not been assigned properly. Step 4. Ascertain the involvement of ions. If the reaction is taking place in water, add H plus or OH minus ions to the expression on the appropriate side so that the total ionic charges of reactants and products are equal. If the reaction is carried out in acidic solution, use H plus ions in the equation. If in basic solution, use OH minus ions. Step 5. Make the numbers of hydrogen atoms in the expression on the two sides equal by adding water, H2O molecules to the reactants or products. Now, Also check the number of oxygen atoms. If there are the same number of oxygen atoms in the reactants and products, the equation then represents the balanced redox reaction. Let us now explain the steps involved in the method with the help of a few problems given below. Problem 7.8. Write the net ionic equation for the reaction of potassium dichromate 6 K2Cr2O7 with sodium sulfite Na2SO3 in an acid solution to give chromium 3 ion and the sulfate ion. Solution. Step 1. The skeletal ionic equation is Cr2O7 2 minus aqueous plus SO3 2 minus aqueous giving Cr3 plus aqueous plus SO4 2 minus aqueous. Step 2. Assign oxidation numbers for Cr and S. Cr2O7 2 minus aqueous, Cr plus 6, O minus 2 plus SO3 2 minus aqueous, S plus 4, O minus 2 giving Cr aqueous, Cr plus 3 plus SO4 2 minus S plus 6, O minus 2 aqueous. This indicates that the dichromate ion is the oxidant and the sulfite ion is the reductant. Step 3. Calculate the increase and decrease of oxidation number and make them equal. From step 2, we can notice that there is change in oxidation state of chromium and sulfur. Oxidation state of chromium changes from plus 6 to plus 3. There is decrease of plus 3 in oxidation state of chromium on right hand side of the equation. Oxidation state of sulfur changes from plus 4 to plus 6. There is an increase of plus 2 in the oxidation state of sulfur on the right hand side. To make the increase and decrease of oxidation state equal, place numeral 2 before chromium ion on right hand side and numeral 3 before sulfate ion on right hand side and balance the chromium and sulfur atoms on both sides of the equation. Thus we get Cr2O7 2 minus aqueous, Cr plus 6, O7 minus 2 plus 3SO3 2 minus aqueous, S plus 4, O minus 2 giving 2Cr3 plus Cr plus 3 aqueous plus 3SO4 2 minus S plus 6 O minus 2 aqueous. Step 4. As the reaction occurs in the acidic medium and further the ionic charges are not equal on both the sides, add 8H plus on the left to make ionic charges equal. Cr2O7 2 minus aqueous plus 3SO3 2 minus aqueous plus 8H plus gives 2Cr3 plus aqueous plus 3SO4 2 minus aqueous. Step 5. Finally, count the hydrogen atoms and add appropriate number of water molecules, that is 4H2O on the right, to achieve balanced redox change. Cr2O7 2 minus aqueous plus 3SO3 2 minus aqueous plus 8H plus aqueous giving 2Cr3 plus aqueous plus 3SO4 2 minus aqueous plus 4H2O liquid. Problem 7.9. Permanganate ion reacts with bromide ion in basic medium to give manganese dioxide and bromate ion. Write the balanced ionic equation for the reaction. Solution. Step 1. The skeletal ionic equation is MnO4 minus aqueous plus Br minus aqueous, giving MnO2 solid plus BrO3 minus aqueous. Step 2. Assign oxidation numbers for Mn and Br. MnO4 minus aqueous, Mn plus 7 plus Br minus aqueous, Br minus 1, giving MnO2 solid, Mn plus 4 plus BrO3 minus aqueous, Br plus 5. This indicates that permanganate ion is the oxidant and bromide ion is the reductant. Step 3. Calculate the increase and decrease of oxidation number and make the increase equal to the decrease. 2MnO4 minus aqueous, Mn plus 7 plus Br minus aqueous, Br minus 1, giving 2MnO2 solid, Mn plus 4 plus BrO3 minus aqueous, Br plus 5. Step 4. As the reaction occurs in the basic medium and the ionic charges are not equal on both sides, add 2 OH minus ions on the right to make ionic charges equal. 2MnO4 minus aqueous plus Br minus aqueous gives 2MnO2 solid plus BrO3 minus aqueous plus 2OH minus aqueous. Step 5. Finally, count the hydrogen atoms and add appropriate number of water molecules, that is, 1 H2O molecule on the left side to achieve balanced redox change. 2MnO4 minus aqueous plus Br minus aqueous plus H2O liquid gives 2MnO2 solid plus BrO3 minus aqueous plus 2OH minus aqueous. B. Half reaction method. In this method, the two half equations are balanced separately and then added together to give balanced equation. Suppose we are to balance the equation showing the oxidation of Fe2 plus ions to Fe3 plus ions by dichromate ions Cr2O7 2 minus in acidic medium, wherein Cr2O7 2 minus ions are reduced to Cr3 plus ions. The following steps are involved in this task. Step 1. Produce unbalanced equation for the reaction in ionic form. Fe2 plus aqueous plus Cr2O7 2 minus aqueous giving Fe3 plus aqueous plus Cr3 plus aqueous, equation 7.50. Step 2. Separate the equation into two half reactions. Oxidation half, Fe2 plus aqueous, Fe plus 2, giving Fe3 plus aqueous, Fe plus 3. Equation 7.51. Reduction half, Cr2O7 2 minus aqueous, Cr plus 6, O minus 2, giving Cr3 plus aqueous, Cr plus 3. Equation 7.52. Step 3. Balance the atoms other than O and H in each half reaction individually. Here, the oxidation half reaction is already balanced with respect to Fe atoms. For the reduction half reaction, we multiply the Cr3 plus by 2 to balance Cr atoms. Cr2O7 2- aqueous giving 2Cr3 plus aqueous, equation 7.53. Step 4. For reactions occurring in acidic medium, add H2O to balance O atoms and H plus to balance H atoms. Thus, we get Cr2O7 2- aqueous plus 14H plus aqueous giving 2Cr3 plus aqueous plus 7H2O liquid, equation 7.54. Step 5. Add electrons to one side of the half reaction to balance the charges. If need be, make the number of electrons equal in the two half reactions by multiplying one or both half reactions by appropriate number. The oxidation half reaction is thus rewritten to balance the charge. Fe2 plus aqueous gives Fe3 plus aqueous plus E minus. Equation 7.55. Now in the reduction half reaction, there are net 12 positive charges on the left hand side and only 6 positive charges on the right hand side. Therefore, we add 6 electrons on the left side. Cr2O7 2- aqueous plus 14H plus aqueous plus 6 electrons gives 2Cr3 plus aqueous plus 7H2O liquid. Equation 7.56. To equalize the number of electrons in both the half reactions, we multiply the oxidation half reaction by 6 and write as 6 Fe2 plus aqueous gives 6 Fe3 plus aqueous plus 6 electrons. Equation 7.57. Step 6. We add the two half reactions to achieve the overall reaction and cancel the electrons on each side. This gives the net ionic equation as 6 Fe2 plus aqueous plus Cr2O7 2- aqueous plus 14H plus aqueous giving 6 Fe3 plus aqueous plus 2Cr3 plus aqueous plus 7H2O liquid, equation 7.58. Step 7. Verify that the equation contains the same type and number of atoms and the same charges on both sides of the equation. This last check reveals that the equation is fully balanced with respect to number of atoms and the charges. For the reaction in a basic medium, first balance the atoms as is done in acidic medium. Then, for each H plus ion, add an equal number of OH minus ions to both sides of the equation. Where H plus and OH minus appear on the same side of the equation, combine these to give H2O. Problem 7.10. Permanganate 7 ion MnO4- in basic solution oxidizes iodide ion I- to produce molecular iodine I2 and manganese 4 oxide MnO2. Write a balanced ionic equation to represent this redox reaction. Solution. Step 1. First, we write the skeletal ionic equation, which is MnO4- aqueous plus I- aqueous giving MnO2 solid plus I2 solid. Step 2. The two half reactions are oxidation half I- aqueous I-1 giving I2 solid I0. Reduction half MnO4- aqueous Mn plus 7 giving MnO2 solid Mn plus 4. Step 3. To balance the I atoms in the oxidation half reaction, we rewrite it as 2I- aqueous giving I2 solid. Step 4. To balance the oxygen atoms in the reduction half reaction, we add 2 water molecules on the right. MnO4- aqueous giving MnO2 solid plus 2H2O liquid. To balance the H atoms, we add 4 H plus ions on the left. MnO4- aqueous plus 4 H plus aqueous giving MnO2 solid plus 2H2O liquid. As the reaction takes place in a basic solution, for 4 H plus ions, we add 4 OH- ions to both sides of the equation. MnO4- aqueous plus 4 H plus aqueous plus 4 OH- aqueous gives MnO2 solid plus 2H2O liquid plus 4 OH- aqueous. Replacing the H plus and OH- ions with water, the resultant equation is MnO4- aqueous plus 2H2O liquid giving MnO2 solid plus 4 OH- aqueous. Step 5. In this step, we balance the charges of the two half reactions in the manner depicted as 2I- aqueous giving I2 solid plus 2 electrons, MnO4- aqueous plus 2H2O liquid plus 3 electrons giving MnO2 solid plus 4 OH- aqueous. Now to equalize the number of electrons, we multiply the oxidation half reaction by 3 and the reduction half reaction by 2. 6I- aqueous gives 3I2 solid plus 6 electrons, 2 MnO4- aqueous plus 4 H2O liquid plus 6 electrons giving 2 MnO2 solid plus 8 OH- aqueous. Step 6. Add two half reactions to obtain the net reactions after cancelling electrons on both sides. 6I- aqueous plus 2 MnO4- aqueous plus 4 H2O liquid gives 3I2 solid plus 2 MnO2 solid plus 8 OH- aqueous. Step 7. A final verification shows that the equation is balanced in respect of the number of atoms and charges on both sides. 7.3.3 Redox reactions as the basis for titrations. In acid-base systems, we come across with a titration method for finding out the strength of one solution against the other using a pH-sensitive indicator. Similarly, in redox systems, the titration method can be adopted to determine the strength of a reductant or oxidant using a redox-sensitive indicator. The usage of indicators in redox titration is illustrated below. 1. In one situation, the reagent itself is intensely colored. Example, permanganate ion MnO4-. Here, MnO4- acts as the self-indicator. The visible endpoint in this case is achieved after the last of the reductant Fe2+ or C2O42- is oxidized and the first lasting tinge of pink color appears at MnO4- concentration as low as 10⁻⁻⁶ moles per dm cube, 10⁻⁻⁶ moles per liter. This ensures a minimal overshoot in color beyond the equivalence point, the point where the reductant and the oxidant are equal in terms of their mole stoichiometry. 2. If there is no dramatic auto color change as with MnO4- titration, there are indicators which are oxidized immediately after the last bit of the reactant is consumed, producing a dramatic color change. The best example is afforded by Cr2O72-, which is not a self-indicator but oxidizes the indicator substance diphenylamine just after the equivalence point to produce an intense blue color, thus signaling the endpoint. 3. There is yet another method which is interesting and quite common. Its use is restricted to those reagents which are able to oxidize I- ions, say for example Cu2. 2Cu2+ aqueous plus 4I- aqueous giving Cu2I2 solid plus I2 aqueous, equation 7.59. This method relies on the fact that iodine itself gives an intense blue color with starch and has a very specific reaction with thiosulfate ions S2O32-, which too is a redox reaction. I2 aqueous plus 2S2O32- aqueous gives 2I- aqueous plus S4O62- aqueous, equation 7.60. I2, though insoluble in water, remains in solution containing Ki as Ki3. On addition of starch after the liberation of iodine from the reaction of Cu2+ ions on iodide ions, an intense blue color appears. This color disappears as soon as the iodine is consumed by the thiosulfate ions. Thus, the endpoint can easily be tracked and the rest is the stoichiometric calculation only. 7.3.4 Limitations of concept of oxidation number. As you have observed in the above discussion, the concept of redox processes has been evolving with time. This process of evolution is continuing. In fact, in recent past, the oxidation process is visualized as a decrease in electron density and reduction process as an increase in electron density around the atoms involved in the reaction. 7.4 Redox reactions and electrode processes. The experiment corresponding to reaction 7.15 can also be observed if zinc rod is dipped in copper sulfate solution. The redox reaction takes place, and during the reaction, zinc is oxidized to zinc ions and copper ions are reduced to metallic copper due to direct transfer of electrons from zinc to copper ion. During this reaction, heat is also evolved. Now we modify the experiment in such a manner that for the same redox reaction, transfer of electrons takes place indirectly. This necessitates the separation of zinc metal from copper sulfate solution. We take copper sulfate solution in a beaker and put a copper strip or rod in it. We also take zinc sulfate solution in another beaker and put a zinc rod or strip in it. Now reaction takes place in either of the beakers, and at the interface of the metal and its salt solution in each beaker, both the reduced and oxidized forms of the same species are present. These represent the species in the reduction and oxidation half reactions. A redox couple is defined as having together the oxidized and reduced forms of a substance taking part in an oxidation or reduction half reaction. This is represented by separating the oxidized form from the reduced form by a vertical line or a slash representing an interface. Example, solid/solution. For example, in this experiment, the two redox couples are represented as Zn2 plus /Zn and Cu2 plus /Zu. In both cases, oxidized form is put before the reduced form. Now we put the beaker containing copper sulfate solution and the beaker containing zinc sulfate solution side by side. Figure 7.3. We connect solutions in two beakers by a salt bridge, a U-tube containing a solution of potassium chloride or ammonium nitrate, usually solidified by boiling with agar-agar and later cooling to a jelly-like substance. This provides an electric contact between the two solutions without allowing them to mix with each other. The zinc and copper rods are connected by a metallic wire with a provision for an ammeter and a switch. The setup as shown in figure 7.3 is known as Daniell cell. When the switch is in the off position, no reaction takes place in either of the beakers and no current flows through the metallic wire. As soon as the switch is in the on position, we make the following observations. 1. The transfer of electrons now does not take place directly from Zn to Cu2+, but through the metallic wire connecting the two rods, as is apparent from the arrow which indicates the flow of current. 2. The electricity from solution in one beaker to solution in the other beaker flows by the migration of ions through the salt bridge. We know that the flow of current is possible only if there is a potential difference between the copper and zinc rods known as electrodes here. The potential associated with each electrode is known as electrode potential. If the concentration of each species taking part in the electrode reaction is unity, if any gas appears in the electrode reaction, it is confined to 1 atmospheric pressure, and further the reaction is carried out at 298 K, then the potential of each electrode is said to be the standard electrode potential. By convention, the standard electrode potential E raised to theta of hydrogen electrode is 0.00 volts. The electrode potential value for each electrode process is a measure of the relative tendency of the active species in the process to remain in the oxidized or reduced form. A negative E raised to theta means that the redox couple is a stronger reducing agent than the H+/H2 couple. A positive E raised to theta means that the redox couple is a weaker reducing agent than the H+/H2 couple. The standard electrode potentials are very important and we can get a lot of other useful information from them. The values of standard electrode potentials for some selected electrode processes, reduction reactions, are given in Table 7.1. You will learn more about electrode reactions and cells in Class 12. Summary. Redox reactions form an important class of reactions in which oxidation and reduction occur simultaneously. Three-tier conceptualization, namely classical, electronic, and oxidation number, which is usually available in the text, has been presented in detail. Oxidation, reduction, oxidizing agent, oxidant, and reducing agent, reductant, have been viewed according to each conceptualization. Oxidation numbers are assigned in accordance with a consistent set of rules. Oxidation number and ion-electron method both are useful means in writing equations for the redox reactions. Redox reactions are classified into four categories: combination, decomposition, displacement, and disproportionation reactions. The concept of redox couple and electrode processes is introduced here. The redox reactions find wide applications in the study of electrode processes and cells. Exercises 7.1. Assign oxidation number to the underlined elements in each of the following species. A. NaH2PO4 P underlined. B. NaHSO4 S underlined. C. H4P2O7 P underlined. D. K2MnO4 Mn underlined. E. CaO2 O underlined. F. NaBH4 B underlined. G. H2S2O7 S underlined. H. KAlSO4 12H2O S underlined. 7.2. What are the oxidation number of the underlined elements in each of the following, and how do you rationalize your results? A. Ki3 I underlined. B. H2S4O6 S underlined. C. Fe3O4 Fe underlined. D. CH3 CH2OH C underlined twice. E. CH3 COOH C underlined twice. 7.3. Justify that the following reactions are redox reactions. A. CuO solid plus H2 gas gives Cu solid plus H2O gas. B. Fe2O3 solid plus 3CO gas gives 2Fe solid plus 3CO2 gas. C. 4BCl3 gas plus 3 LiAlH4 solid giving 2B2H6 gas plus 3 LiCl solid plus 3 AlCl3 solid. D. 2K solid plus F2 gas giving 2K plus F minus solid. E. 4NH3 gas plus 5O2 gas giving 4NO gas plus 6H2O gas. 7.4. Fluorine reacts with ice and results in the change H2O solid plus F2 gas giving HF gas plus HOF gas. Justify that this reaction is a redox reaction. 7.5. Calculate the oxidation number of sulfur, chromium and nitrogen in H2SO5, CrO7 2- and NO3-. Suggest structure of these compounds. Count for the fallacy. 7.6. Write formulas for the following compounds. A. Mercury 2 chloride. B. Nickel 2 sulfate. C. Tin 4 oxide. D. Thallium 1 sulfate. E. Iron 3 sulfate. F. Chromium 3 oxide. 7.7. Suggest a list of the substances where carbon can exhibit oxidation states from -4 to +4 and nitrogen from -3 to +5. 7.8. While sulfur dioxide and hydrogen peroxide can act as oxidizing as well as reducing agents in their reactions, ozone and nitric acid act only as oxidants. Why? 7.9. Consider the reactions A. 6CO2 gas plus 6H2O liquid gives C6H12O6 aqueous plus 6O2 gas. B. O3 gas plus H2O2 liquid gives H2O liquid plus 2O2 gas. Why it is more appropriate to write these reactions as A. 6CO2 gas plus 12H2O liquid giving C6H12O6 aqueous plus 6H2O liquid plus 6O2 gas. B. O3 gas plus H2O2 liquid giving H2O liquid plus O2 gas plus O2 gas. Also, suggest a technique to investigate the path of the above A and B redox reactions. 7.10. The compound AgF2 is unstable compound. However, if formed, the compound acts as a very strong oxidizing agent. Why? 7.11. Whenever a reaction between an oxidizing agent and a reducing agent is carried out, a compound of lower oxidation state is formed if the reducing agent is in excess, and a compound of higher oxidation state is formed if the oxidizing agent is in excess. Justify this statement giving 3 illustrations. 7.12. How do you account for the following observations? A. Though alkaline potassium permanganate and acidic potassium permanganate both are used as oxidants, yet in the manufacture of benzoic acid from toluene, we use alcoholic potassium permanganate as an oxidant. Why? Write a balanced redox equation for the reaction. B. When concentrated sulfuric acid is added to an inorganic mixture containing chloride, we get colorless, pungent, smelling gas HCl, but if the mixture contains bromide, then we get red vapor of bromine. Why? 7.13. Identify the substance oxidized, reduced, oxidizing agent and reducing agent for each of the following reactions. A. 2AgBr solid plus C6H6O2 aqueous giving 2Ag solid plus 2HBr aqueous plus C6H4O2 aqueous. B. HCHO liquid plus 2AgNH32 plus aqueous plus 3OH minus aqueous giving 2Ag solid plus HCOO minus aqueous plus 4NH3 aqueous plus 2H2O liquid. C. HCHO liquid plus 2Cu2 plus aqueous plus 5OH minus aqueous giving Cu2O solid plus HCOO minus aqueous plus 3H2O liquid. D. N2H4 liquid plus 2H2O2 liquid giving N2 gas plus 4H2O liquid. E. Pb solid plus PbO2 solid plus 2H2SO4 aqueous giving 2PbSO4 solid plus 2H2O liquid. 7.14. Consider the reactions 2S2O3 2 minus aqueous plus I2 solid giving S4O6 2 minus aqueous plus 2I minus aqueous. S2O3 2 minus aqueous plus 2Br2 liquid plus 5H2O liquid giving 2SO4 2 minus aqueous plus 4Br minus aqueous plus 10H plus aqueous. Why does the same reductant, thiosulfate, react differently with iodine and bromine? 7.15. Justify giving reactions that among halogens, fluorine is the best oxidant and among hydrohalic compounds, hydroiodic acid is the best reductant. 7.16. Why does the following reaction occur? XeO6 4 minus aqueous plus 2F minus aqueous plus 6H plus aqueous giving XeO3 gas plus F2 gas plus 3H2O liquid. What conclusion about the compound Na4XeO6 of which XeO6 4 minus is a part can be drawn from the reaction? 7.17. Consider the reactions A. H3PO2 aqueous plus 4AgNO3 aqueous plus 2H2O liquid gives H3PO4 aqueous plus 4Ag solid plus 4HNO3 aqueous. B. H3PO2 aqueous plus 2CuSO4 aqueous plus 2H2O liquid gives H3PO4 aqueous plus 2Cu solid plus H2SO4 aqueous. C. C6H5CHO liquid plus 2AgNH32 plus aqueous plus 3OH minus aqueous giving C6H5COO minus aqueous plus 2Ag solid plus 4NH3 aqueous plus 2H2O liquid. D. C6H5CHO liquid plus 2Cu2 plus aqueous plus 5OH minus aqueous, giving no change observed. What inference do you draw about the behavior of Ag plus and Cu2 plus from these reactions? 7.18. Balance the following redox reactions by ion-electron method. A. MnO4 minus aqueous plus I minus aqueous, giving MnO2 solid plus I2 solid in basic medium. B. MnO4 minus aqueous plus SO2 gas, giving Mn2 plus aqueous plus HSO4 minus aqueous in acidic solution. C. H2O2 aqueous plus Fe2 plus aqueous, giving Fe3 plus aqueous plus H2O liquid in acidic solution. D. Cr2O7 2 minus plus SO2 gas, giving Cr3 plus aqueous plus SO4 2 minus aqueous in acidic solution. 7.19. Balance the following equations in basic medium by ion-electron method and oxidation number methods, and identify the oxidizing agent and the reducing agent. A. P4 solid plus OH minus aqueous, giving PH3 gas plus HPO2 minus aqueous. B. N2H4 liquid plus ClO3 minus aqueous, giving NO gas plus Cl minus gas. C. Cl2O7 gas plus H2O2 aqueous, giving ClO2 minus aqueous plus O2 gas plus H plus. 7.20. What sorts of information can you draw from the following reaction? Cn2 gas plus 2OH minus aqueous, giving Cn minus aqueous plus CnO minus aqueous plus H2O liquid. 7.21. The Mn3 plus ion is unstable in solution and undergoes disproportionation to give Mn2 plus, MnO2 and H plus ion. Write a balanced ionic equation for the reaction. 7.22. Consider the elements Cs, Ne, I and F. A. Identify the element that exhibits only negative oxidation state. B. Identify the element that exhibits only positive oxidation state. C. Identify the element that exhibits both positive and negative oxidation states. D. Identify the element which exhibits neither the negative nor the positive oxidation state. 7.23. Chlorine is used to purify drinking water. Excess of chlorine is harmful. The excess of chlorine is removed by treating with sulfur dioxide. Present a balanced equation for this redox change taking place in water. 7.24. Refer to the periodic table given in your book and now answer the following questions. A. Select the possible nonmetals that can show disproportionation reaction. Select 3 metals that can show disproportionation reaction. 7.25. In Ostwald's process for the manufacture of nitric acid, the first step involves the oxidation of ammonia gas by oxygen gas to give nitric oxide gas and steam. What is the maximum weight of nitric oxide that can be obtained starting only with 10 grams of ammonia and 20 grams of oxygen? 7.26. Using the standard electrode potentials given in the table 8.1, predict if the reaction between the following is feasible. A. Fe3 plus aqueous plus I minus aqueous. B. Ag plus aqueous plus Cu solid. C. Fe3 plus aqueous plus Cu solid. D. Ag solid plus Fe3 plus aqueous. E. Br2 aqueous plus Fe2 plus aqueous. 7.27. Predict the products of electrolysis in each of the following. 1. An aqueous solution of AgNO3 with silver electrodes. 2. An aqueous solution of AgNO3 with platinum electrodes. 3. A dilute solution of H2SO4 with platinum electrodes. 4. An aqueous solution of CuCl2 with platinum electrodes. 7.28. Arrange the following metals in the order in which they displace each other from the solution of their salts: Al, Cu, Fe, Mg, and Zn. 7.29. Given the standard electrode potentials, K plus / K equals 2.93 V, Ag plus / Ag equals 0.80 V, Hg2 plus / Hg equals 0.79 V, Mg2 plus / Mg equals minus 2.37 V, Cr3 plus / Cr equals 0.74 V. Arrange these metals in their increasing order of reducing power. 7.30. Depict the galvanic cell in which the reaction Zn solid plus 2Ag plus aqueous gives Zn2 plus aqueous plus 2Ag solid takes place. Further, show 1. Which of the electrode is negatively charged, 2. The carriers of the current in the cell, and 3. Individual reaction at each electrode.